A designer chooses the values of fluid flow rates and specific heats in such a manner that the heat capacities of the two fluids are equal. A hot fluid enters the heat exchanger at 100 degrees centigrade and leaves at 80 degrees centigrade. The cold fluid enters the heat exchanger at 40 degrees centigrade. Assuming the designer uses both parallel and counterflow heat exchangers for the same conditions, find out the ratio of the logarithmic mean temperature difference of parallel flow heat exchanger to counterflow heat exchanger. So here the designer chooses the values of fluid flow rate and specific heats in such a manner that the heat capacities of both the fluids are equal. Here heat capacity is nothing but mass flow rate into specific heat of the fluid is nothing but heat capacity of the fluid. Here heat capacities of the both hot fluid and cold fluid are equal, but we know that heat gained by the cold fluid is equal to heat lost by the hot fluid, that is delta Th is equal to mCp cold fluid into delta T cold fluid. So here mCp of both the fluids are equal, so that heat capacity, that is nothing but heat capacity of two fluids are equal, so that mCp get cancelled and delta Th is equal to delta Tc. Here delta Th is 20 degrees centigrade and delta Tc must be 20 D, so that the outlet of the cold fluid is at 60 degrees centigrade. Now here the designer uses both parallel flow and counterflow heat exchangers. Now first draw the parallel flow heat exchanger. So let us say this is at 40 degrees centigrade and this is 100 degrees centigrade. Hot fluid enters at the 100 degrees centigrade and leaves at 80 degrees centigrade, and here cold fluid enters at 40 degrees centigrade and leaves at 60 degrees centigrade. So the difference at the exit is equal to 20 and difference at the inlet is equal to 60. So let us say this is delta T1 and this is delta T2. So it is equal to delta T2. Now consider another one, that is counterflow heat exchanger. So here counterflow heat exchanger, hot fluid enters at 100 degrees centigrade and leaves at 80 degrees centigrade, and here cold fluid enters at 40 degrees centigrade and leaves at 60 degrees centigrade. So the difference between in this position is 40 and at this position also 40. So now here delta T1 is equal to delta T2 in case of parallel flow heat exchanger, that is equal to 40 degrees centigrade, so that here logarithmic mean temperature difference is equal to just 40 degrees centigrade. But in case of parallel flow, LMTD is given by delta T1 minus delta T2 by ln of delta T1 by delta T2. So here it is 60 minus 40 by ln of 60 by 40, which gives a value of 36.4. and now the ratio between LMTD of counterflow to, sorry, here it is parallel to counterflow, which is equal to 36.4 by 40, which is nearly equal to 0.91. So that in the option, the right option is C. C is the right answer. The transition Reynolds number for flow over a flat plate is 5 into 10 power of 5. What is the distance from the leading edge at which transition will occur for the flow of water with a uniform velocity of 1 meter per second? For water, take kinematic viscosity is equal to 0.858 into 10 power minus 6 meter square per second. So here this is the case flow over a flat plate, and after a certain distance flow gets translated to the turbulent, that is up to certain region it will be laminar, and after that it will be translated region, transition region, and after that it is a turbulent region. So here the given Reynolds number for the flow over a flat plate for the transition. So at this point transition will occur, and here we will have to find out the distance from the leading edge at which transition will occur. Leading edge is nothing but at the entrance of the plate. So the flow at the entrance of the plate is nothing but leading edge, and the liquid leaves the plate is nothing but trailing edge. So here it is, we will have to find out this distance. So, and we know that the Reynolds number is given by rho Vd by mu, where rho is the density of the fluid and V is velocity of the fluid. D is the diameter, or for the flat plate it is given as length of the plate. D is diameter for the diameter for the tube. If it is a internal flow, then it is diameter of the tube. If it is external flow, then you will have to take characteristic length of the tube. That is nothing but here it is x, and here mu is nothing but dynamic viscosity. And but we don't know the values of density of the fluid and dynamic viscosity, so that we can write it as V into x is a characteristic length, and here mu by rho gives kinematic viscosity. So we have the values of all these things: kinematic viscosity, velocity of the fluid, and Reynolds number at the transition region. So that here you can have the distance from the leading edge, x is equal to Re into nu by V. So here Re is 5 into 10 power of 5, and kinematic viscosity is 0.858 into 10 power of minus 6, and velocity of the fluid is 1 meter per second. So it gives a value of 0.43 meters. So in the option, the right option is B. Company uses a certain part at a rate of 2500 units per year. Each unit costs 30 rupees. The ordering cost is 130 rupees per order. It is estimated that the carrying cost of average inventory is 10%. Determine the rupee value of the optimum order to be placed each time. So here we will have to calculate the rupee value of the optimum order quantity. So that is nothing but economic order quantity. So here first, in the given data, a company uses a certain part at a rate of 2500 units per year. Let us say R is equal to 2500 units per year, and each unit costs 30 rupees. So CO is, this is unit cost. CU is equal to 30 rupees, and the ordering cost 130 rupees per order, and it is estimated that the carrying cost of average inventory is 10%. So here the ordering cost is 130 rupees per order, and the carrying cost of the average inventory is 10%, that is 0.1. So here carrying cost is equal to CU into I, which is equal to 30 into 0.1. So here 3 rupees per unit per year. So here number of orders per year is given by RCC by 2C0, which is equal to 2500 into 3 by 2 into 130. So it is 5.37 orders per year, and UOQ is equal to 2500 by n, that is R by n. So it is equal to 465 units. So this is the economic order quantity, but we will have to calculate the rupee value of the optimum order to be placed each time. So the rupee value is equal to rupee value of optimum order or economic order quantity is equal to, so 465.5 into CU, that is 30, so which is equal to 13,965 rupees. So in options, the right option is A. A is the right answer. Which of the following statements regarding PERT is incorrect? So in the given options, it is a statistical technique which makes decisions is the wrong statement for regarding the PERT. So B is the right option.